Good morning, students. So in the last class we discussed about the dipole moment and electric field to the dipole on the equatorial line, axial line, and horizontal point, right? So now today we are going to discuss about electric potential to the dipole. Electric potential to the dipole. Let us take directly the point at a general point. Let us calculate here. And after that we will discuss about when the dipole is placed in a field, how force or torque acts on this. We discuss all those topics. So let us see this potential to a dipole. So potential to a dipole at a general point direct I am taking here. Let us say this is a midpoint here, so let us say this is positive charge and this is a negative charge and this is a positive charge here. Suppose say we are going to find potential at this point. So we need to find potential at this point here. So which is at a distance so far from the center. Right? So now this is I'm drawing this line from this negative charge and from the positive charge. And next here we extend this line here and we draw the normals. Similarly, let us draw one more normal here. I am giving some names so that we can express this triangles in terms of names here. Let us take this is A, B, C, and this is our point D. That means at point D we are going to calculate the potential. And this is one point here. Let us take this is L and this is L, right? And this angle we are taking it as theta. That means we are taking this AB distance as 2L here. That is the length of this dipole. And the CD distance we are assuming as from C to D. So at that point D we are going to calculate the potential. So potential at the point D is nothing but potential due to positive charge plus potential due to negative charge, because we know scalar potential is a scalar quantity. So just potential due to the combination of charges means we can add the potential due to individual charges. So here two charges is there, two charges over there. One is positive and other is negative charge. So we can add the potential due to positive charge and the potential due to negative charge to get the potential at that point. So for that we need to write this distance here. Suppose if you are writing potential due to negative charge, we need to write AD distance, and potential due to positive charge if you want to write this BD distance we need to write. So for that what I am doing simply here is we are going to express the distance in terms of this R here. R is distance of our required point from the center of the dipole, like our previous axial line and equatorial line calculation. There also we mentioned R is measured from the center. So now here this length is L and this length is also L, and if this angle is theta, I can consider this angle as theta. Now we are drawing this normal A and means now I can say that N D distance will be same as that of AD, because I am drawing normal from this. And so now simply from C to D we already know C to D we are assuming it as R. Now simply we need to write this NC distance. So from the triangle that we can calculate from the triangle ANC, cos theta is equal to, so we need this side here, so this is our right angle. So cos theta is equal to, I can write this as NC by CA. Therefore, NC is equal to CA is nothing but L cos theta. Therefore, we can write this as AD is equal to NC plus CD. So, which I can write as L cos theta plus R. This is our AD distance, right? This is AD. And now similarly, we can calculate this BD distance. So for writing that BD distance, again I am drawing this normal here, so that we can write this BD distance and MN distance both are equal. And to calculate this MN also, just we need to write this CM distance. And that is also similar to this, we can write here. So from the triangle, I am taking like BMC. And so that we can write as again cos theta is equal to MC by BC. So this MC is equal to L cos theta we can write. And therefore I can write this BD distance. This distance we can express it as CD minus MC. So which is nothing but R minus L cos theta we can write. So that is our BD distance. So as we calculated the distance of positive charge and negative charge from that point, now we can write the potential. So directly I am writing the net potential there. So net potential at point D. So that can be written as potential due to positive charge plus potential due to negative charge. So we should add the potential due to individual charges. So here potential due to negative charge means we know potential due to negative charge is negative. So then when we are substituting the values, we will get the negative sign there. So therefore it is potential due to positive charge is this one. So I can write this as KQ by BD. That BD is nothing but R minus L cos theta, right? So it is plus K into minus Q R plus L cos theta. So potential due to negative sign, when we know already, in case of potential calculations, when you are writing the potential due to negative sign, negative charges, it will be negative. So we need to substitute the negative sign there. So I am taking this KQ common. Then LCM direct I am taking here R plus L cos theta. That means this LCM term will be R square minus L square cos square theta you get the product of these two terms. So in the numerator the first term you will get like this minus R minus L cos theta you will get. So you can simplify that further. So this is I will write here, it may not be covered in this. This I will write here somewhat closer to this. So it will be R minus L cos theta. Right? Now it may be visible. So this is KQ into, now let us simplify this. The dot term will be cancelled. 2L cos theta by R square minus L square cos square theta. And we know this 2L into Q we can write as dipole moment, the product of this charge and distance between the two charges. So but this P is equal to Q into 2L. Therefore potential at a general point we can write as K into P cos theta by R square minus L square cos square theta. This is general expression for this potential due to dipole. So just we are writing the potential due to positive charge plus potential due to negative charge. That is potential due to positive charge is KQ by and the distance of positive charge we need to write BD value. That BD value we calculated here R minus L cos theta. And similarly the potential due to negative charge here R plus L cos theta. Just let us take here. This is the negative sign here. Potential due to negative charge is negative. Take that KQ term outside, then you will get negative sign here and take LCM. And if you simplify this, you will get this expression. Just here we are replacing this Q into 2L as with the dipole moment P. So P into, in terms of P we are writing Kp cos theta by R square plus L square cos square theta you will get. That's the expression for a potential due to a dipole. And now in case of a short dipole if I consider. So again we know short dipole means L value is very small when compared to that of R. So that L square terms can be neglected here. So I will write for the short dipole. this potential we can write as Kp cos theta by r square. So this is potential due to a short dipole at a general point. That means this L square term will be, this term will be negligible. So we are neglecting this term. Then this Kp cos theta by r square will be. So this is potential due to a short dipole at any general point. So at any general point, this how the situation will be like this. Suppose if this is the dipole here at this point, at any general point. So at this point, say C, then we are writing this total potential calculation here. In case of short dipole, we can represent like this. And now here, for example, if I am specifically, this is directly we have mentioned it for a general point. Now let us see the cases if you are taking for a axial, for a point on the axial line and for a point on the equatorial line. So I can write this as, so I will write here for an axial point. For axial point, this theta value will be equal to, for axial point, theta value is equal to 0. Axial line is that this theta value, this line only we need to consider a point, then theta value will be 0. So if we substitute that theta value, therefore this V axial is equal to Kp by r square. Cos theta value will be 1 you will get if you substitute that theta value. Then Kp by r square you will get. That is the potential due to a short dipole for an axial point. Even if you are for the long dipole, if you want to write, you can mention this point directly here. That means that theta value 0 you can directly substitute in that expression. So this is general dipole I am writing here. Then you can write this expression as Kp by r square minus L square unit. If you are taking it as a, if it is not a short dipole, then r and L are comparable. If it is a short dipole, then we can directly write like this, right? And for an equatorial line, if I write, so for equatorial line, if I write, then you can take the theta value as 90 degrees. So then potential on the equatorial line is, then cos theta value is 90 degrees here, cos 90 is 0. Even for the long dipole also you get this equatorial as 0. This is for axial, right? That means for any point on the equatorial line, this dipole moment will be 0. Potential due to the dipole will be 0 for any point on the equatorial line. That means we can conclude that as one equipotential. On equipotential line or equipotential surface we can consider that, because for any point on this line the potential will remain same, which is 0. That means suppose it is our equatorial line here. So at any point on this equatorial line, it may be here or you may consider here or you may consider here or at any distance from the center. At any distance from the center, the potential will be 0, because if you are taking a point for example here, then potential due to negative charge and potential due to positive charge both are equal in magnitude, and but signs will be opposite, and so that they will cancel with each other. So the net potential will be 0, and so that this equipotential equatorial line is equipotential. So equipotential line we can say the line is. So that means that is equipotential line here. Or equipotential surface you can consider, because such a large number of lines you may consider here. So that is an equipotential surface I am saying. So that means equatorial line, that plane you can consider, that line you can consider as equipotential surface, because at any point on that line the potential will be, resulting potential will be 0 only. So that is the potential calculations. So on for a general point and as well as for this equatorial and axial. So for equatorial line if you want to say, you can directly say it as 0. For the axial point it is Kp by r square you can write for short dipole. And next let us see this is simply potential calculation due to this dipole here. And next let us see the effect of electric field on this dipole. That is dipole, when dipole is placed in, say, first we discuss about uniform electric field, later we discuss about non-uniform electric field. So I can say this as So I will write directly as torque acting on dipole in uniform electric field. That is dipole placed in uniform electric field. So they know the meaning of uniform electric field. So uniform electric field means the field whose magnitude as well as direction remains same at any point in the space. So at any point in the space, the magnitude of electric field will be same as well as its direction is also same at any point. Then the field is said to be uniform field. Like suppose I am taking a uniform field is there like this, and we can represent such a uniform field by equidistant and parallel lines, right? So such as suppose uniform electric field of intensity P is there. Now in such a uniform electric field, suppose I am considering a dipole is placed here. So this is say minus 2 and this is plus 2. A dipole is placed here. This is of length of this dipole is say L, and this angle I am taking as theta. And so now that such a dipole is placed like this. This is a negative charge and this is a positive charge. Now think about this positive and negative charges. Let us discuss about first to say positive charge. Positive charge, that means it is a point charge. A point charge is placed in uniform electric field. So whenever a charge is placed in uniform electric field, we know that there will be some force acting on it, and that force is in the direction of electric field if the charge is positive. If it is negative charge, then it will be opposite the direction of electric field. So here it is positive charge, so its force acting on this will be in the direction of electric field, whose magnitude I can say EQ. The direction of that force is like that. And on this negative charge, it is opposite the direction of electric field, and so its force we can write as EQ, opposite to that. And so that if I ask the net force acting on the dipole, what is the net force acting on the dipole? Two forces are acting on the dipole. One is in the direction of dipole and other is opposite the direction of dipole. Then the net force acting on the dipole will be, easily you can say that these two forces will cancel with each other. So net force acting on the dipole is 0. So you should remember that whenever a dipole is placed in the uniform electric field, net force acting on the dipole is 0. Always 0, whatever may be the orientation of this dipole. So whenever it is placed in uniform electric field, net force is always 0. You should remember in uniform electric field. And but here you can observe that these two forces will consistently get coupled, because due to this force the dipole is turning like this in say anti-clockwise direction, and this is also producing in the same direction here. And so these two forces will produce a couple on this dipole here. The couple is nothing but two equal and opposite forces. So these two equal and opposite forces producing the turning effect in the same direction, and so that we can call them as couple. And so now we need to calculate the moment of this couple. So the force expression first I am writing here. Force on each charge is F is equal to EQ. Net force on dipole is is 0. That is important point here. And so next I am writing the moment of couple, which we can call it as a net and torque. Net torque or moment of couple. So that can be written as magnitude of one of the force into perpendicular distance between them. So here the magnitude of this one of the force is nothing but EQ into this perpendicular distance we need to write here. Suppose I am taking this as A, B, and this is the point C. So that AC distance we need to write here. This R perpendicular is nothing but our AC. So So that AC value we can calculate by using this triangle here. So here I can set this angle as theta. So that here I can set this angle will be theta. So from triangle here I am writing here from triangle ABC. You can write sin theta value. Opposite side is AC by AB. Therefore, this AC is equal to AB sin theta. And we know that this is nothing but our perpendicular distance here. So AC is equal to AB is nothing but 12. So 12 sin theta we can write here. So let us substitute this value. Therefore, it is EQ into 12 sin theta. Right? Now, this E into Q is nothing but dipole moment. Our dipole moment is nothing but product of the charge and distance between them. And therefore, this value we can write as tau is equal to PE sin theta we can write. It is the magnitude of this tau. Because here just we are using this, but P is equal to Q into 12 that we are replacing there. So P is sin theta we can write. So if you want to express it in vector form, this in vector form, then we can write it as tau bar is equal to P bar cross E bar. So there is a dipole moment, and here you can observe this. Why we are writing P bar cross E bar means the direction of this torque here. The direction of the torque is this dipole is turning like this. So the direction of this torque is this out of the plane here. Or you can use the force at perpendicular distance transferred rule also. Now the P bar and E bar direction now we can use here. Our P bar is along this direction. This is our P bar from negative to positive charge, and E bar is along this direction here, right? This is our P bar and this is E bar. So then P bar cross E bar. P bar cross E bar will be out of the plane. So that we can write this in vector form as P bar cross E bar. So that is the torque acting on the dipole when it is based in uniform electric field. In vector form we can express like this, and its magnitude is nothing but P sin theta we can write, where P is the dipole moment and E is the electric field, the electric field strength. And the theta, there you should remember about the theta clearly. There theta is angle between P bar and E bar. So this is nothing but theta here, what we are taking here. That theta is actually the angle between P bar and E bar, that you should remember here. P bar is along this direction and E bar is along this direction. So these are P bar and E bar vectors here. And so this theta is angle between P bar and E bar. So that is the torque expression acting on this. So you should remember that now. When a dipole is placed in uniform electric field, no force acts on this, no force acts on the dipole, but there may be a torque acting on this dipole. The torque expression is given like this. And sometimes they will mention that when a dipole is placed in uniform electric field, net force must be 0, and the torque may or may not be 0. Net force and the torque must be 0. Torque must be 0, force may or may not be 0. Such a type of confusing options may be there. So you should remember it clearly. Net force is always 0 if the field is uniform. I am saying this is about for uniform electric field. When a dipole is placed in uniform electric field, net force is always 0. And about the torque, it depends on the orientation of this. You can't say that net torque is not 0 for all the cases. So here torque may be 0 also. From this expression we can observe this. For example, if I consider this theta value as 0 or 180, then the torque is 0. Even though it is placed in uniform electric field, torque may be 0. That means torque may or may not be 0. That depends on the configuration of this dipole. How the dipole, that is configuration in the sense what is the angle between P bar and E bar. That depends on that whether torque is 0 or not. But definitely you can conclude that net force on the dipole is always 0 when it is placed in the uniform electric field. So this is for uniform electric field only, you should remember. Now let us take the possibilities when the dipole torque acting on the dipole is 0 and when it becomes maximum here. It's a simple derivation only, you can understand this easily. And again I am saying all these derivations, the field, potential, like torque derivations, all these derivations will be there in magnetic dipole also. So if you understand understand this easily, then you can derive those derivations easily by yourself. Once the dipole is introduced for you, magnetic dipole, you can do all these derivations there for the magnetic dipole also. And now let us say when the torque is minimum and when the torque has maximum as its maximum value. So first time I can mention that when theta is 0 or theta is 180, then torque has its minimum value. So that minimum value is nothing but 0. That means you will get E bar and P bar, both are in the same direction. Then here this theta value will be 0. So this is the meaning of this theta, 0 angle. P bar and E bar both are in the same direction. If they are in opposite direction, if E bar is like this but the dipole is placed like this, then here this angle is 0. Either in this case or in this case, there is no torque acting on this, because those forces will pass through the center only. If suppose a dipole is placed parallel to this, this is a positive charge and this is a negative charge here, right? Then force acting on the positive charge will be like this and force acting on the negative charge will be like this. So clearly you can say that one force is acting like this, other force is acting down. So clearly you can say that these two forces cannot rotate the dipole, right? These two forces are just pulling the charges away from each other, but those forces cannot rotate the dipole here. And so that's why we are saying this torque is 0. And same in case of this also, just the charges will be reversed. That's only the forces will be along that line only will get. So that is why there is no torque acting on the dipole when it is 0 or 180. And the next point we can conclude here. When theta is equal to 90 degrees, 580, then torque has maximum value, and so its maximum value is nothing but P into E. So that means when electric field is like this and a dipole is placed like this, so that this theta value is pi by 2 here, then maximum torque acts on the dipole in that position when they are normal to each other. So it is a torque acting on the dipole when it is placed in uniform electric field. So when it is placed in non-uniform electric field, the force acting on the dipole may not be 0. And torque acting on the dipole also may not be 0. Again, there we can't conclude that whether it is 0 or not. That depends on how that field is changing, how that non-uniform field is present here. But simply you can say that non-uniform, when the dipole is placed in non-uniform electric field, non-uniform electric field means simply that you can observe this. We will discuss actually that later. We will derive an expression for force acting on the dipole when it is placed in non-uniform electric field, and we will discuss some problems also based on this. Just I am explaining theoretically here. If it is a uniform, non-uniform electric field, for example, let us consider. A non-uniform electric field means there may be chances like the field may vary in direction, but magnitude will remain same. That is one possibility. And the other possibility is the field may have the same direction, but magnitude of the field may be different at different points. That is another possibility. Or both magnitude and direction both may change. So that is another possibility. So that means the non-uniform means simply it is not uniform. It is not same at all points, both in magnitude and direction. If either magnitude is changing or direction is changing, or both magnitude or direction is changing, then we can call it as non-uniform electric field. So simply, for example, I am taking the field is same in direction, but magnitude is changing, for example. So here a dipole is placed here. Let us say here the dipole is placed like this. Let us say this is some negative charge and this is a positive charge here. And here electric field is say E1. So E1 into Q will be there like this. And here electric field is E. Here I am assuming that field is same in direction, but simply magnitude is varying. Just that example I am taking here. So then here you can observe that the force direction, the field direction is like this. So field on the positive charge, the force on the positive charge is E1 into Q, and force on the negative charge is E2 into Q. Now these two are not equal. The magnitude of these two forces are not equal, and so net force may not be zero. There may be some net force acting on the dipole, and these forces may also constitute the torque. And so when the charge is when the dipole is placed in non-uniform electric field, there may be net torque and net force acting on the dipole. So both will be there. Both non-zero values may be there. You can't conclude that because there may be different possibilities for this field over there. Whether field is changing magnitude, changing direction, or both magnitude and direction are varying. But we will discuss that later. And we will derive an expression for that. Force acting on the dipole when it is placed in uniform electric field, non-uniform electric field. Next here, from the torque expression, let us derive an expression for potential energy. The potential energy of the dipole when it is placed in uniform electric field. So potential energy of a dipole. Potential energy of a dipole means, like suppose say here the initially the electric field is like this, the direction of this electric field, and the dipole is placed like this, for example. And we mentioned this, the torque expression previously. What we mentioned is, so there it is important to note about this role of this torque here, P sin theta. The role of this P sin theta is, whenever the dipole is not in the direction of the field, not in the direction of uniform field, this torque will develop, and this torque will try to rotate it brings the dipole into the direction of the field, into its own direction. That is the role of this dipole. That means if the dipole is placed like this, then there will be some torque acting on this. Because of the torque, this dipole will bounce like this. That means the external field will try to turn the dipole into its own direction. When it turns into its direction, when the dipole and field or both are in the same direction, then torque acting on that is 0. That means if you are initially placing the dipole like this, if you are placing the dipole and electric field in the same direction, then there is no torque acting on this, right? Torque acting on that will be 0. So whenever some angle exists here, some non-zero theta is there here, other than that 0 or 180, then some torque will act on this, and that brings the dipole into its own direction there. That is the role of this torque. Is it clear? That is the role of this P sin theta. Whenever this dipole is other than this field direction, then this torque will develop, and this torque will turns the dipole into the direction of this electric field. And that is simply, we can say, that is the reason why a freely suspended magnet always aligns north and south direction. Right? In magnetism we will discuss actually. In magnetism, that means here some horizontal component of magnetic field will be there here along this towards north. And if you are placing a magnet other than this north south direction, then such a similar torque will develop in that due to that horizontal component of Earth's magnetic field, and that turns the magnet into the direction of this field. That some horizontal component of magnetic field is along north south direction. And so then magnet will turns into this north-south direction there. So that is the reason why that magnet always aligns in north-south directions there. So similar to that, if you disturb the dipole from its field direction, automatically it comes back to that position because of that. And so that now let us define the potential energy here. So the potential energy we can define it as, so generally we know when you are defining the gravitational potential energy, we take some reference. Like suppose if an object is placed on the ground, for example, then the amount of work done in lifting the object to a particular height h, the amount of work done in lifting the object and placing the object at a height h, that amount of work done will store as potential energy in that. So simply we can define the potential energy like that in gravitational potential energy means. Now similarly here we define that potential energy as amount of work done in turning the dipole from the given angle through the given displacement. So that means from the initial 90 degrees to that angle, that we define as the potential energy for this. And so potential energy is nothing but, and before going to this potential energy, I think if you write the work done expression, then you can easily understand this. So first before that, let us note this one, work done. Work done on the dipole. So if you write this work done expression, then you can understand that the dipole expressions. Like let us say this is electric field, P4 is like this. Now the work done is nothing but when you are displacing the dipole to the small angle theta, let us say, or first let us consider d theta, then some work is done here. So that amount of work done we can write as work done for small angular displacement d theta. So d double is equal to, now this is work done by torque here. So tau into d theta I am writing here. We are displacing the dipole slowly through an angle d theta. That means, for example, here it is, we are displacing it through the small angle d theta here. This angle d theta, suppose we are defined. We are displacing the dipole. Then here you can observe that we are writing work done means two types of work done will be there here. We are displacing the dipole slowly in the sense, like if you are displacing the object from the ground to certain height, then what are the forces acting on this object? When you are lifting an object from ground to this height h, then gravitational force mg is acting downwards. Then we should apply an external force in upward direction, right? So that it is displacing. And how much force we are applying here when the body is displaced slowly? The force which is exactly equal to the gravitational force, or which is exactly equal to the weight of this object. That amount of force we should apply. If you are applying less than that, the object won't rise. If you are applying more than that, the object will rise with some acceleration, increasing velocity. But we are not displacing with acceleration. We are displacing it slowly. We are displacing it slowly means exactly the force, downward force must be equal to upward force. So here also two torques will be there here. One is due to the field, due to the electric field, and other is due to the external. Now when you are displacing the dipole slowly, then these two torques will be equal. Electric field, torque due to electric field and torque due to this external agent will be, they are equal in magnitude. Because if you release the dipole here, then in the previous discussion we discussed that dipole automatically turns into the direction of, no need of doing any work, external work actually. Automatically it turns into the direction of field with increasing velocity if you are releasing from the position. But here why we are applying some external torque, or why external work is done required here is, we are displacing without any gaining kinetic energy. We are not interested to gain the kinetic energy of the dipole. So we should apply some opposite torque. Just if we release it, automatically this dipole will turn into the direction of the field. But its kinetic energy will increase. Here it is having some maximum kinetic energy if we release it. But we are not interested to displace the dipole with such increase in kinetic energy. We are displacing it slowly. That is the case what we are defining. If we want to displace it slowly, then definitely an opposite torque is required here. And so that is external torque we are explaining, and the external torque we are applying here. So that this external torque and torque due to field both are equal in magnitude. So that this torque means I can directly take the torque due to the field. Torque due to the field means which we derived previously. And this is similar to our F into ds. So a small amount of work done in linear motion we can write as F into dr or ds we can write, small displacement. So here similarly in rotatory motion, angular work done is nothing but tau into d theta. Now the tau is nothing but P sin theta we can write. This is our tau expression here. So this is actually work done, this expression, but what we are saying, these two are equal. So instead of this external torque also we are writing that down, P sin theta 1. So to get the total work done, we need to integrate this. So this is, now we are writing total work done. Total work done in the sense work done by the external agent only. If it is a field, they will ask work done by the field. Here we are writing work done by the external agent only. Total work done to rotate dipole from theta 1 to theta 2, or you may consider like initial angle to final angle, theta initial to theta final. And so now this integration we need to do for this. So then integral of P sin theta d theta. And P is constant, you can write outside. So then cos theta is minus cos theta you will get here, and limits are from initial to final. So therefore this work done I can write this as P of cos theta initial minus cos theta final. This is the amount of work done here. Work done by the external agent in displacing the dipole from theta initial to theta final. There theta initial and theta final means what those angles? Angle between P bar and E bar. Angle between this electric field and this dipole material. That initial angle to final angle you need to write. And here there may be some confusion regarding this theta here. For example, here I am giving an angles like this. Initially P bar is like this and E bar is like this. That means initially they are perpendicular to each other. Now it is drawn through an angle through 30 degrees. Right? Now what is the work done by the external agent? So now in this what is theta 1 and theta 2 values? Theta 1 is 90 degrees because initially it is making initially it is perpendicular to this field. So theta 1 is 90 degrees. Theta 2 is not 30 degrees here. Theta 2 is 60 degrees. This angle always we need to write. Angle between P bar and E bar. It is turned through 30 degrees. When it is turned through 30 degrees, the angle between P bar and E bar will become 60 degrees. So that 60 degrees we should take it as theta 2 value or theta final here. Right? So theta initial is 90 degrees and theta final is 60 degrees. So that is the importance of the theta initial and theta final. Right? So there are the initial and the final angle between P bar and E bar we need to write. So this is work done by the external agent. If for example if they ask work done by the field, just the negative of this value we need to write. That we discussed from the beginning of potential itself. Work done by the field and work done by the external agent, they are equal in magnitude, just the sign is opposite when the particle is displaced slowly. So here the dipole is displaced slowly, and so that we can write work done by the external agent is equal to work done by this negative of work done by the field we can write here. So this what we are calculating is work done by the external agent. So that is work done expression here. So P into E into cos theta initial minus cos theta final we can write. And next here, now let us come to this potential energy. Now once this work done is completed, then potential energy calculations will be easy for us. Now this potential energy is defined as the amount of work done in displacing the particle, displacing the dipole from the initial normal position to any angle theta. This is our initial position. This is the final. Final angle may be any angle. So that amount of work done is taken as stored as potential energy in the dipole. So here, like in our gravitational potential energy, we take some reference. So when the object is on that reference, we take that potential energy as 0. When it is above the potential, above the reference by a distance h, for example, then we write the potential energy as mgh. If it is below the reference line, then we write the potential energy as minus mgh. So like that, there we are taking some reference there. So if the object is on the reference, we say potential energy is 0. So similarly here, this is taken as a reference here. The normal position is taken as a reference here. So when they are normal to each other, then we can say the potential energy of the system is 0. So then for any angle, from this initial position to any angle theta, the amount of work done will store as potential energy in that. So now write the definition of this potential energy first. So the first note the dipole work done by the work done on the dipole in uniform electric field, and next is potential energy of the dipole. So write the definition of this potential energy. The amount of work done, by the external agent, in displacing the dipole, from its initial normal position to any angle theta, any angle theta is stored as potential energy in the system, is stored as potential energy in the system. That means here theta initial is 90 degrees and theta final is theta you can consider. So directly you can substitute, or you can write the work done again this calculation here. What we are saying is potential energy is equal to representing with the U, the amount of work done in displacing from theta initial 90 degrees to theta final in the angle theta. You can directly substitute in our previous formula for work done. We derived already cos theta initial minus cos theta final into P. Now you can directly substitute in that. Just I am doing the work done integration again. So then this is nothing but our PE sin theta d theta. This is from theta initial 90 degrees to theta final theta. Therefore you can write this potential energy as minus PE cos theta unit, right? So which you can also write this expression as, this is a potential energy expression. So you can also write this expression as, or you can also express this as minus of P bar dot E bar. Because this PE cos theta you can write as P bar dot E bar. So either you can express like this PE cos theta, or you minus PE cos theta, or you can express like this minus P bar dot E bar. So it is a potential energy expression now. So torque expression is PE sin theta. Work done expression is, work done with external agent expression is PE into cos theta initial minus cos theta final we need to write. And this is a potential energy expression minus PE cos theta. And now from this can you say when the potential energy of the dipole is minimum and when the potential energy is maximum? Can you say those values? So when theta value is, for example, if I consider it as 0, then potential energy will be minimum when theta value is 0, because when theta value is 0 then minimum potential energy is minus PE you will get. This is our first point we can mention. Next, when theta is equal to 180 degrees, so when theta is equal to 180 degrees, this will be maximum. So which is plus E. This is the maximum potential energy. Theta is 90 means we can set as a reference. So that value will be 0. So when theta is 0, potential energy of the system is minimum, so which is minus P. When theta is maximum, then potential energy of the system will be plus P. So which is the maximum value. Theta is 180 degrees please. So actually we can mention all those in a simple, we can represent all those conditions in a simple diagram. So let us see this. This is say electric field and the dipole. Now they are in the same direction, that means here. So here the theta value is 0, they are parallel to each other. Now therefore this torque is minimum, and so that is 0. PE sin theta, so that sin theta value is 0. Now the potential energy is minimum, so that potential energy is minus PE we can write here, right? But it's when they are parallel to each other. And suppose they are anti-parallel to each other. This is suppose say E bar and a P bar is like this. That means now here the angle is 180 degrees and the torque is still minimum, that is 0. But potential energy is maximum here, that is plus P, right? Now suppose if they consider if they are perpendicular to each other, E bar is perpendicular to this P bar, then theta value will be 90 degrees, and the torque is maximum torque here, which is P, and the U value will be 0. Because it is not a maximum or minimum, it's a reference point actually. And now from this we can actually discuss the type of equilibrium of the dipole here. We know the types of equilibrium of a dipole, right? Types of equilibrium: stable equilibrium, unstable equilibrium. So we know such a types here. So when the dipole is, when the particle is said to be in stable equilibrium, recently also we discussed here regarding the field. That means when the two charges are placed and in between the two charges we are placing a third charge. We discussed about the stability of that charge. And so now here also we need to discuss that. So again I am revising that. Simply you can remember that a stable equilibrium is like this: a ball and a particle is placed inside. Then this is stable equilibrium. So unstable equilibrium means the particle is inverted like this, and we are, that means ball is inverted like this, and the particle is placed above this. So this is unstable. And neutral means the particle is placed on the ground itself, on the same horizontal level. So here the importance is, if you are displacing the particle slightly and release it, then it comes back to that position here. And so that is nothing but we call stable equilibrium. In stable equilibrium, potential energy is minimum. And in unstable means, if a small disturbance is there, then particle moves away from that equilibrium position and it never comes back here. And potential energy of this particle is maximum in this. So that is unstable. And neutral means if you displace the particle slightly from the equilibrium position, there is no neither tendency to move back or not to move away from that position. And potential energy of this particle will remain constant in that. Now basing on that you can discuss which position is stable and which position is unstable here. And so now here torque is 0 and here also torque is 0. So that we can conclude that these two may be equilibrium, that means these two positions are equilibrium positions. But here it is not equilibrium, right? Because it is some torque is acting on it. Now in this we need to discuss which is stable or which is unstable equilibrium. We need to discuss in these two cases, first two cases. So in this now we can say that potential energy is minimum. From that you can decide it is a stable equilibrium, or otherwise we can verify by displacing the dipole slightly. If it is coming back to that position, then it is stable equilibrium. If it doesn't come back, that means it moves away from that equilibrium position, then it is unstable equilibrium. We can discuss here. So now here we discussed already. Suppose if the dipole is, suppose if the field is like this, if I am displacing the dipole like this, if I place the dipole from this position, I am displacing slightly to this position, to the small angle, then what will happen? Then some torque will develop here. We are releasing from this. When you release from this, some torque will act on this, and because of the torque, the dipole again comes back here. That is nothing but the torque expression P sin theta what we discussed now. So that because of the torque, the particle, this dipole will comes back to this position here, and so that is said to be stable equilibrium. And so that because it is coming back, when the dipole is displaced slightly from equilibrium, it is coming back, and so that it is stable equilibrium position. And whereas if you are taking like this, now the electric field is like this, and now the dipole is opposite to that. So from that position, for example, I am displacing it slightly. Initially it is along this direction. Now I am displacing slightly like this. Then now the dipole is not in the direction of the field here. Then again this P sin theta torque will act on this. And because of the torque, again the dipole will turn like this. That means it is not coming back to its position. It is moving away from this equilibrium position and finally it reaches this position here. And so that whenever a slight disturbance is there from this, it turns into the direction of the field like this. That means it is moving away from that. And so that we can consider this as unstable equilibrium. So theta is 180 is unstable equilibrium positions. So those are the simple values you need to remember here. When theta is 0, importance of theta is 0, 180 and 90 degrees. So theta is 0 is torque 0, potential is minimum and a stable equilibrium. Theta 180 means torque 0, potential energy is maximum and it is unstable. And theta is 90 means torque maximum and potential energy is 0. So those are the values you need to remember regarding that. And here as I said, some problems may be there based on this when the particle, when the dipole is released from certain angle theta. So just you may mention that as one note here or a point next after this. Suppose this is the direction of electric field. I am releasing the dipole from this position here. Now I will ask what is the angular velocity of the dipole when it reaches the direction of the field. That means from this position it is turning like this. It is turning in the direction of this dipole here. We are releasing from rest. Now here it is traveling with some velocity, angular velocity. We need to calculate the angular velocity of this dipole. That means we are releasing the dipole when it makes an angle theta with the field. Now the question is we need to find its velocity when it comes into the direction of the field. So simply we need to apply the conservation of energy. If we know the potential energy expression, then we can write simply conservation of energy. By torque equation, from the torque equation we can find angular acceleration, from that angular velocity we can do. It's a lengthy calculation, it's integration we need to use. Simply you can apply the conservation of energy between these two. Is it clear what I am calculating? The dipole is released from this position when it makes an angle theta with the direction of electric field. We know because of this torque P sin theta, this dipole starts rotating into the direction of the field. If you release that, it won't travel with the constant velocity. It travels with the increasing velocity. Angular acceleration will be there because some unbalanced torque is there. So here we need to calculate velocity when it reaches to this position. And actually, wherever you are releasing, velocity will become maximum when it becomes into the direction of the field. Because in that position, potential energy is minimum. Potential energy is minimum means kinetic energy will become maximum in that position if you are releasing the dipole. And so now here, simply I can write by conservation of energy. If they ask find velocity in this position, maximum velocity in this position, simply we can apply the conservation of energy. This is the equation I am writing here. So that by conservation of energy, initial energy is equal to final energy we can write. So that initial means initial kinetic energy plus initial potential energy is equal to final kinetic energy plus final potential energy we need to write. So initial kinetic energy is 0 because we are releasing from rest. And initial potential energy we need to write as minus PE cos theta we need to write. Because it is making some angle theta, right? Now final kinetic energy we need to write as rotational kinetic energy we need to write here half I omega square, where I is moment of inertia of the dipole. According to the given arrangement, we need to write the moment of inertia. Like suppose two point charges are given. mr square plus mr square we can write, where r is the distance of the point charge from the center. So the 2mr square we can write here. So that is depends on the given configuration. If a rod is given for example, then ml square by 12 we can write about the center of mass. So that depends on the configuration, whether it is point charge distribution is given or any other arrangements are given. So I is moment of inertia of the given arrangement about its center. And final potential energy is minus PE, because PE cos 0. So that minus PE you will get. And from this simply we need to write this half I omega square value. Half I omega square value is nothing but PE of, I am taking that PE common, 1 minus cos theta. So from this you can calculate the velocity there. So that is a way of proceeding sir for such type of problems. Just whenever such a energy related question or velocity related questions are there, simply you can apply the conservation of energy. The other method is also there for this, by writing torque equation. This I will explain that, but it's a lengthy method. You can proceed by conservation of energy method. Like I can write for any general position, I can write this torque is equal to P sin theta. I can write this. We can write as torque I alpha is equal to P sin theta. I can write. Therefore, alpha is P by I into sin theta. We can write. And this alpha value we can write as omega into d omega by d theta. We can write. Right. Similar to our acceleration, we can write as v into dv by dt. So similar to that, that angular acceleration we can write like this. So it is P by I into sin theta. So we can integrate this. So it is P by I into sin theta d theta. This is from initially 0, final angular velocity, and this is from theta to 0, final angle is 0. That one in that case. So like that also we can do. But it is a unnecessary calculation will be there. That's a simple method. You can simply apply the conservation of energy. So then in such a type of problems you can solve, you can proceed like this. So that is potential into the dipole and potential energy, torque acting on this and potential energy. And next some numericals will be there based on this, numerical problems based on this dipole, and when dipole is placed in non-uniform electric field, how to calculate the force, and all those problems we will discuss later. So today you can complete the problems based up to this, based on this dipole up to this topic, like potential energy, torque, electric field calculations. So those problems you can complete here. So in the next we discuss some problems based on this dipole, and then we discuss about this dipole placed in non-uniform electric field, how to find the force acting on the dipole when it is placed in non-uniform electric field. Thank you.